So now we are going to discuss about the how AI agent memory works. What are the different layers into that one, and how this is related to the human brain, and how one perfect memory or the context can be built with our previously understanding the concept of taxonomy, ontology, semantic layers, and knowledge management system. So this is a very this diagram describes a runtime architecture for agent memory. Okay, so one user input is coming, then how the different types of memories are there: working memory, episodic, semantic, procedural, and meta memory. So there are 5 layers of memories are present here, and each memory layer has a different epistemic character. That means each one sits differently in the taxonomy, ontology, and the knowledge graph hierarchy. So let me walk through this systematically. First is that all these 5 layers are not just storage buckets. Okay, they differ in 3 fundamental ways: how they are written, how they are read, and what kind of knowledge they hold. Right? So here knowledge means I am talking about some kind of fact, some kind of user related fact, some kind of historical informations, and how the decision has been taken, how the reasoning was used, how the reasoning was derived, all those kinds of information I am referring this knowledge. So don't get confused with the knowledge means the retrieval, augment, generation, and those kind of knowledge. So there is a different when I am using this knowledge terminology at this context. So working memory is transient. The first thing is coming that the working memory, and this is transient in context and resets. Episodic memory is an next is coming episodic memory. So what is episodic memory? Episodic memory is that historical or the informations about the user, how these are structured in a very chronological order. Okay, so when I say chronological order, that means when a new information comes, that will get appended only. Okay, so what comes under this one? It is like trace of what across the session that will get append with this episodic memory. Then next one is come that semantic memory. Okay, so semantic memory is a typed entity store built by extraction. It is like different kinds of entities are getting involved while generating the response for the user query. And procedural memory is a kind of it gets maintained in a version wise, and it's kind of skilled registry built by reflection. So it reflects, okay, what are decisions taken, which tools were called, and what are the different reasoning steps were taken, whether something went wrong, something went good. So all these kinds of skill development, skill registry built by reflection. And meta memory is an offline control plane which is managing all these 4 through different kind of archival, means it is archiving. So more information is coming, it is archiving and storing. Deduplication, it is removing some duplicate information. Deprecations means if something is outdated, then it is deprecating that one. And decay means, okay, something is not required, then it is removing that one. So this is called that life cycle. So this matters, this complete system matters for knowledge representation, because those 4 dimensions like write pattern, read pattern, epistemic type, and life cycle map directly onto how we should model each layer in an ontology. So if we go, let's try to understand what are the different types of layers. 5 layers of knowledge management system. You can say that memory or the knowledge management system here. It's not RAG. Okay, this is not, don't get confused with this is RAG. Don't get confused. And the So what gets includes in this episodic memory? I'm just some kind of traces, right? That means it's a chronological order. So some kind of traces, trace elements. Then it is like retrieval queries, retrieval query, session information, all this. And then the next one is about semantic. So entity, here it will be coming entity, and entity attributes, entity attributes. Entity means what? It's a kind of different classes, different data attributes, something related to that. And when it comes to entity type, then extraction job, some kind of extraction job, something like job, right? And then procedural memory. So what is coming under procedural memory? It is skill version. So we are maintaining some kind of skill version. What are the different version it is used? And some kind of reflection, we are using some reflections, and some kind of tags types category or something like. And then it is coming that meta memory. So what meta memory says? Meta memory is a archive. So it will manage the complete life cycle of all these four memory layers. So it has some kind of archive policy, decay policy, deduplication, then it is deprecation events, something like all these will be coming here. So what you observe is that I am maintaining one kind of hierarchy. So first is that agent memory. Inside that one, these 5 layers of memory, and under each layer, what are the different subclasses can be created in order to define that specific memory layer. So I have created one kind of hierarchy. So that means what is a taxonomy layer. So these are all called the taxonomy layer. Taxonomy layer of agent memory, right? So next what will come is and it gives the vocabulary. It says what kind of things exist in the system, definitely what kind of different attributes we discussed in order to explain a specific memory layer. So it gives you the vocabulary. It says what kinds of things exist in the system. It does not say what those things mean or how they are related. That we will come to know in our next layer, that is ontology layer. Ontology layer of agentic memory, you can say. So in this case, in this layer, what will do? Design becomes here, it will become interesting. Why? Because each memory layer requires different ontological commitments. Working memory ontology, what? Working memory is bounded by the context window. Okay, working memory is a context window. When the context window means it tries to reach the maximum context window size, then it has to concat that one. It is the memory size, okay, and that is a formal constraint, not just the implementation details. So working memory has exactly one active context window because that is transient. A context window has a max token capacity of type integer. So it will be like, for example, working memory, it will be having one context window, one active context window, and one context window has a maximum token capacity of type integer, and one active context window, I am saying CW, has a maximum token capacity, max token capacity. So what you understood from here? It is like relationship, how the active, what is WM, we came to know. A term, okay, a term contains tool calls. Is a term is part of exactly one working memory. A compaction event is triggered when, so a compaction event is triggered when token usage approaches max token capacity. So what you understood from here? Compaction event, it comes under under meta memory. Okay, so how, when a term is part of exactly one meta memory, so when we are putting questions one by one, user query, we are putting at first user query came, LLM responds something, then we on top of that again we are trying to know something else, so again the user put another query. So these are term, second term, third term, and these terms are part of the working memory only, because in the same session these terms are getting created. And the compaction event, how to compact, is triggered when token usage approaches max token capacity. This is kind of rule. So here what we are trying to understand, the key ontological relationship here is the temporal containment. Okay, because that is intransient. A term contains tool calls, intermediate reasoning steps, and a response, and those things have a strict ordering. So ontology must encode that ordering as a sequence relation, not just association. So what it does, the ontology, what it does, it say ontology must encode the ordering as a sequence relation, not just an association, not just an association. Okay, so ontology, before also we had described that it will contain some kind of relationship, and we saw that how these relationships are getting captured here. The life cycle rule, working memory state is destroyed at session end. In ontological terms, every instance of working memory has a lifespan scoped to a session. Nothing in working memory persists to a subsequent session except through explicit write operations to one of the persistence layer. Okay, until and unless we don't write it explicitly to one of the persistent layers, then it will be getting destroyed in that session itself. The next one is coming about episodic memory. So here it's append only, and that is the central ontological commitment. No trace is ever modified after it is written. This means the ontology must encode the distinction between a write operation that creates a new trace and an update operation that does not exist itself. So what are the relationship here? A trace records exactly one turn. A trace records exactly one turn. Right? A trace has a timestamp. A trace has a timestamp. A session identifier. A session identifier. And then a content representation. And a content representation. That means what is the content generated? That representation. Traces are retrieved by three mechanisms. Okay, traces will have how many? It is similarity, time and scope, and the ontology must encode these as distinct retrieval strategy. So what are the traces are retrieved by three mechanisms. that is similarity, and then next comes semantic memory. So semantic memory is an entity store, and every entity in semantic memory with a typed attributes. Entity types form their own taxonomy. For examples like person, organization, concept, event, artifact. So this is a sample healthcare ontology system. You can say like that. These are some entities. Okay, these are getting displayed under classes. So each entity, you can say each class can be entity. Admission, allergy, department, this is person, and person can be of many type, right? This person can be patient, this can be doctor, this can be administrator, and inside that, if we go to the data properties also, these are some data properties, that means which are getting represented by the columns in a RDBMS system. Okay, some address date. So these are all different kinds of entities, and this semantic memory that describes the entity type. So when it comes, entities relate to other entities through a type relationships. When we are saying like this is the object properties. Okay, so administered by, inside that you can see that administered by, and here domain and the ranges, that means vaccination. Domain means domain, relationship, and then ranges. So vaccination administered by nurse. Okay, in this way we are maintaining the semantic relationship between various entities. And the ontological rule from the diagram, semantic memory is built by extraction job that read episodic traces. Relationship between various entities, right? So semantic memory instances are not populated by direct user input, they are populated by extraction job processes, and that take episodic traces as input and produce entity assertion as output. So I am saying is, when I say extraction job, it is very much mandatory to understand all these things, concepts now, because these will be helpful later when we are actually coming up with the system design session of this 5 layers memory system, right? So understanding these concepts are very much important. So next part is that when I say that procedural memory is a version skill registry. Skill has one or more skill versions. So what I can say that a skill has one or more skill versions. So again relationships came. A skill version is an authoritative procedure. A skill version is an authoritative procedure for a tax type. If a tax has to be, in order to perform a tax to be performed, we should have some kind of skill version, and at a point of time. The system retrieves skills by tax type. System retrieves skills by tax type. Okay, and so these are all kinds of relationships are there. So procedural memory is built by reflection passes over past episodes. This encodes a dependency on both episodic memory and reflection process, and a reflection process reads a set of traces, identified patterns that constitute a reusable skills, writes a new skill version. Without procedural memory, what happens? The agent can never grow itself. It can never understand what are the actions taken, the reasoning capacity. It cannot maintain. Okay, it repeats the same with the procedural memory. It repeats the same reasoning from scratch for every similar task. The ontology must encode this compounding relationship like a skill reflection pass R over the traces T1, T2, T3, T4, etc. and carries a provenance back to the traces. You just recall what we had discussed while building a recall provenance system. So it should be able to trace back to the required source. And what is the freshness of that required source? Whether it has taken from the recently updated information or some stale information, right? So next is coming that meta memory. So in this meta memory, this is what is that meta memory? Meta memory is the controlling layer of all. So here what happens, no, it does not store any domain knowledge, it stores the policies and operations that govern the other four layers. Okay, what it stores? It stores the policies and governance rules that operate other four layers, right? So the classes will be what we had defined. What are the different classes? It will be like archive policy, decay policy, archive policy, decay policy, etc. Deduplication, and then what is that? Decay, um, deprecation, compression strategy, threshold trigger, right? Compression, here you can say like that, compression strategy. When we are doing compression, when the maximum token capacity, when the token usage getting approaches maximum token capacity, then we have to compress that. So some kind of compression strategy, threshold trigger, and all those concepts. So the ontological relation, every archive policy applies to one or more target layers. A decay policy defines a decay function over time. So what are this? It is like every archive policy applies to one or more memory layer. Okay, each time archive policy, if it says like that, no, semantic memory needs to be archived, its context use, token usage is approaching the max token capacity, then what will do, it will apply that archive policy, something like that. Okay, if something do duplication, that also it will do. A decay policy defines decay function over time and a threshold below which a trace or entity is archived or deleted. A threshold trigger fires a meta memory operation when a uh, monitored memory crosses a defined value. This critical design point that the critical design point is that without meta memory, the diagram states the stack rots. In ontological terms, the other four layers have unbounded growth, no resolution of contradictions, and no mechanism for deprecating stale procedures. And meta memory is the controlling layer that governs the life cycle of all this complete memory system, right? So we are done with ontology layer. So next is, what is that? Semantic layer. Semantic layer. So semantic layer. So here what it says, that semantic model is where you resolve the questions that the ontology leaves open. That means semantic layer gives some meaning. For examples, if I say like that, what counts as a complete trace? Okay, we need to understand the complete trace. The trace should not be incomplete. What counts as a complete trace? So what it happens? A trace is complete when it contains a user input, when it contains an user input planning step, at least one tool call with some reasoning and a response and a no tool call with some reasoning, or no tool call. You can say no tool. It's not mandatory that always a tool call will happen, but if the answer can be if the response can be generated itself without calling the tool, then no call tool is needed. But in that case, giving one justification with a justification, okay, giving one justification, okay, why this there was no tool call was needed. So all these kinds of reasoning things is coming here. And so incomplete traces are flagged, not discarded, because even failed episodes carry information for reflection, because it will say why this was failed. Okay, similarly, what is the definition of a skill? A skill is a reusable procedure that has been extracted from at least two independent episodic traces performing the same task type. Okay, when is an entity considered? All these kinds of some kind of semantic meaning definitions I am giving. At first I gave definition what counts as a complete trace. The second one I gave that what is the canonical definition of a skill. And the third one, if I say like that, when is an entity considered resolved, right? So when is an entity considered resolved? Two entity candidates are resolved when the identifier attributes overlaps on at least one canonical identifier type, or when a semantic similarity score across their attribute sets exceeded defined threshold confirmed by a resolution job. Okay, so these definitions are not present in the diagram that I had shared here, this diagram, okay, but they are the organizational level commitments that system must make before knowledge graph can operate reliably. So knowledge graph is a connecting layer of all the three layers, and it is the implementation layer. So if I go down, you can see that all these definitions here, and this is also the biological analogy how a human brain works. Okay, and this all this context memory layer, they are just a duplication of human memory, a human brain, how memory works in the human brain. So next step is about knowledge graph layer. Okay, so after that where all the above becomes operational in a production agent memory system, the knowledge graph would encode such as specific agent instances with their associated memory layer instances. So, for example, specific skill instances with their version history, provenance traces, and applicable tax types will be, all those related things will be managed as part of the node and edges. Then specific entity instances with their resolution history, attribute values, extraction jobs. For example, here I can write down that specific entity instances with their version history, this is resolution, means how those are resoluted, and then it is like that different kind of extraction, because here those are getting through some extraction jobs, and then some kind of attribute values, and it is like that so that a specific that produced them, and all these etc. produced all these are produce that specific task. Okay, so this is getting stored into the KG layer. The graph also encodes the cross-layer dependency. So episodic trace feeds extraction job, feeds entity in semantic memory, and then episodic trace feeds reflection pass feeds skilled version in procedural memory. So all those kinds of relationships, those we have derived here, all those will be coming into the KG layer. So when we say KG layer, it is the implementation. Okay, this is the physical, and the physical layer we can say in a database. So there actually we are storing all these informations in the form of some individuals. So when it says to the individuals, or if I say that individuals, then these are all these kinds of informations present, right? So here I say that aspirin, description is aspirin, and it is a type of analgesic. So individuals means it is the actual data present. Okay, bed 1, when I say that bed refers to the bed 1, 2, 3, bed types bed, then bed 1, 2, 3, 4 are there. So this is the in the form of individuals, we are storing those into the KG layer, and that is in the form of some kind of nodes and relationship. And then this is a kind, from here this specific context or the memory is getting generated and getting fed to the LLM applications. So we understood about all these layers. Now that when we say about in future sessions we have to come up with a design principle that ties all of this together, then what we will be discussing there? A 5 memory layers, and these 5 memory layers are not parallel. They are hierarchical dependent, and the direction of dependency matters for knowledge presentations. Working memory is the source of all new information. Episodic memory is the persistent record of working memory activity, and then semantic and procedural memory is derived from the episodic memory through extraction jobs, reflections, etc. Meta memory is the governance layer for all of these 4. So any knowledge representation design that treats these as 5 independent stores will fail to capture the system's actual behavior. They are very tightly coupled to each other. Okay, and the ontology must encode the dependency chain, because that chain is the mechanism by which the agent learns, compounds, and maintains the quality of its own knowledge over time. Okay, so in these systems we got the conceptual knowledge. In future sessions we'll be covering how we have to convert all these memory systems into a knowledge graph systems. Thank you then.